This program will provide the basic understanding of wet scrubber methods used in air pollution capture of particles and various wet scrubber control devices. We will cover what is wet scrubbing and how do wet scrubbers work, types of wet scrubbers and their design and components, proper operating conditions and causes of decreased performance, performance monitoring. In wet scrubbing processes, liquid or solid particles are removed from a gas stream by transferring them to a liquid. That liquid is usually water. However, if gaseous pollutants are also being removed, it may be an aqueous solution that contains chemicals selected to react with the absorbed contaminants. Most wet scrubbing systems operate with particulate collection efficiencies over 95%. There are many equipment designs for contacting the liquid with the contaminated gas stream. The capability of a particular design can be approximated from the gas stream pressure drop across the scrubber. In general, higher pressure drops indicate more aggressive contact between the liquid and the gas stream, causing smaller particles to be collected with greater efficiency. Scrubbers with pressure drops less than about 5 inches of water are capable of efficiently removing particles greater than about 5 to 10 micrometers in diameter. These are referred to as low-energy wet scrubbers. Medium-energy wet scrubbers have pressure drops from 5 to 25 inches of water. These collectors are capable of removing micrometer-sized particles, but are not very efficient on submicrometer particles. Removal of submicrometer particles requires significant energy input, ranging from 25 to over 100 inches of water, depending on the particle size. These collectors are referred to as high-energy wet scrubbers. Not all scrubber designs will conform to these generalized categories. Collectors that may collect smaller particles than their pressure drop would include electrostatically enhanced scrubbers and condensation growth scrubbers. The spray tower is a low-energy device and is the simplest wet scrubber used for particle collection. It consists of an open vessel with one or more sets of spray nozzles to distribute the scrubbing liquid. Typically, the gas stream enters at the bottom and passes upward through the sprays. The particles are collected when they impact the droplets. This is referred to as countercurrent operation. Spray towers can also be operated in a cross-current arrangement. In cross-current scrubbers, the gas flow is horizontal and the liquid sprays flow downward. Cross-current spray towers are not usually as efficient as counter-current units. The tray tower is a medium-energy scrubber and consists of a vertical column with one or more trays mounted horizontally inside. The simplest tray is a perforated plate that is referred to as a sieve tray. Other tray designs include impingement trays that have small impingement targets above each perforation to enhance gas-liquid contact, bubble cap trays that can operate over a wide range of gas and liquid flow rates without adversely affecting collection efficiency, and valve trays that have liftable valves or caps that improve gas-liquid contact when the gas flow rate varies. Tray scrubbers are vulnerable to solids accumulation and plugging problems. Regardless of the tray design, all of these units operate in a similar manner. The contaminated gas stream enters at the bottom and flows upward through the holes in the plates. The liquid enters at the top of the tower, flows across the tray, and then through a downcomer to the tray below until it reaches the bottom of the tower. The function of the trays is to disperse the liquid into droplets and the gas stream into bubbles, creating the gas-liquid contact necessary for particle collection. Packed bed scrubbers are another type of medium-energy collector. Packed bed collectors spread the liquid over packing material in order to provide a large surface area for particle impaction. There are many designs for the packing materials, but they all have large surface area while maintaining open areas for the gas flow. Although they are usually made of plastic, metal and ceramic packings are available when plastic cannot be used. Like spray towers, packed beds are classified according to the relative direction of the gas and liquid flows. In the countercurrent design, the liquid is introduced at the top of the tower using sprays or weirs and flows downward over the packing material. The contaminated gas stream enters at the bottom of the tower and flows upward through the packing. Because of limitations in the amount of liquid that will move downward against the upward gas flow, this orientation is susceptible to plugging when the concentration of solid particles is high. In the cross-flow scrubber, the gas stream flows horizontally through the packed bed, while the liquid flows down through the packing material. Because greater amounts of liquid can be used in this arrangement, the collector can handle high concentrations of solid particles without plugging. In some designs, the particles are charged before entering the packed bed in order to increase collection efficiency. These devices are referred to as ionizing wet scrubbers. A medium energy device used for the collection of liquid particles is the fiber bed scrubber. In this collector, the contaminated gas stream flows horizontally through one or more vertical mesh pads composed of randomly interlaced fibers or woven fibers. The density of the fibers controls the size of droplets that are removed. Scrubbing liquid is sprayed continuously or intermittently on the inlet side of each pad. The most common high-energy wet scrubber is the Venturi, although it can be operated as a medium-energy scrubber. In the fixed-throat Venturi, the gas stream enters a converging section where it is accelerated toward the throat section. In the throat section, the high-velocity gas stream strikes liquid streams that are injected at right angles to the gas flow, shattering the liquid into small drops. The particles are collected when they impact the slower-moving drops. Following the throat section, the gas stream passes through a diverging section that reduces the velocity. Some particle collection also occurs in this section. One variation of the standard Venturi scrubber is the wetted approach design. In this design, the scrubbing liquid is introduced at the beginning of the converging section using overflow weirs and a central spray nozzle. This is done to wet the converging section and protect it from particle erosion. Another variation is the variable throat Venturi. Since the scrubbing energy is a function of the gas velocity in the throat, Venturis that can change their throat dimensions are used when the gas flow rate from the process varies. The position of the adjustable throat mechanism is usually set to maintain a fixed pressure drop across the collector. In all wet scrubbers, the process of contacting the gas and liquid streams results in entrained droplets. Since these droplets contain the contaminants, they must be removed before the gas stream exits the unit. This is referred to as mist elimination or entrainment separation. The most common mist eliminators are chevrons, mesh pads, and cyclones. Chevrons are simply zigzag baffles that cause the gas stream to turn several times as it passes through the mist eliminator. The liquid droplets are collected on the blades of the chevron and drained back into the scrubber. Mesh pads are made from interlaced fibers that serve as the collection targets. A cyclone is typically used for the small droplets generated in a Venturi scrubber. The gas stream exiting the Venturi enters the bottom of a vertical cylinder tangentially. The droplets are removed by centrifugal force as the gas stream spirals upward to the outlet. To review, wet scrubbers for particles are classified by energy usage levels, which include low energy usage, medium energy usage, and high energy usage. The common types of air pollution control wet scrubber systems for particles are spray tower wet scrubbers, tray tower wet scrubbers, packed bed wet scrubbers, fiber bed wet scrubbers, and Venturi wet scrubbers, all of which are followed by mist eliminators or entrainment separation methods that remove final or exit droplets. This is done with chevrons, mesh pads, and cyclones. The control efficiency a device has in capturing contaminants is affected by particle size, and pressure drop. There are several operating problems that can occur in wet scrubbing systems. The most common of these include the following: inadequate liquid flow, improper liquid pH, liquid reentrainment, poor gas-liquid contact, plug nozzles, beds, or mist eliminators, corrosion. The ability to evaluate potential problems during a field inspection will depend on how well the system is instrumented. Most large systems are well instrumented. However, smaller systems may have limited instrumentation. Performance evaluation of these systems will be difficult unless measurements of important parameters are made. There should be two goals in any field inspection. First is to evaluate the source's compliance with any rule-specific monitoring requirements and with the provisions of the Title V permit. In addition, parameters that influence performance should be evaluated to see if there are shifts from the baseline values that can indicate reduced collection efficiency. The most direct indicator of system performance is the opacity of the outlet gas stream. However, since the gas stream is usually close to saturation at the outlet of the scrubber, the presence of condensing moisture may make the observation difficult. For the same reason, opacity monitors are not typically used on wet scrubbers, since it is not possible to differentiate between light scattering due to particles and that due to water droplets. Therefore, less direct indicators of performance are typically used. Perhaps the best indicator of adequate gas-liquid contact is the difference in temperature between the inlet and outlet of the scrubber. If that temperature difference has decreased, it is likely that the collection efficiency has also gone down. For example, a higher than normal temperature at the outlet of a scrubber may indicate a decreased liquid flow rate. The liquid flow rate into the scrubber is also important. If the flow rate is being monitored, the value during the inspection should be compared to the baseline or permit value. A decrease in the liquid flow rate without a proportional decrease in the gas flow rate will usually cause a decrease in the collection efficiency. If the flow rate is not being monitored, other indicators can be used. Indirect indications of decreased liquid flow rate include a decrease in the pump discharge pressure or an increase in the pressure in headers supplying spray nozzles. Increased pressure in a supply header is usually due to plugging of the nozzles, which reduces the liquid flow rate. The pH of the inlet and outlet liquid should be evaluated. An inlet pH above 10 indicates a potential for scale accumulation that can plug nozzles, packed beds, and trays, reducing liquid flow rates and impairing gas-liquid contact. An outlet pH below 6 can cause severe corrosion of metal components. Changes in scrubber pressure drop can occur for several reasons. Increased pressure drop across a packed bed or tray scrubber may indicate plugging of the bed or trays. Increased pressure drop on a Venturi scrubber may be caused by increased liquid flow rate or by adjusting a variable throat damper to a more closed position. A decrease in the pressure drop across a tray scrubber may indicate warped or collapsed trays, while for a Venturi scrubber, it may be caused by decreased liquid flow rate or by adjusting a variable throat damper to a more open position. Similarly, the pressure drop across the mist eliminator provides an excellent indicator of its physical condition. For mist eliminators that are used to remove the relatively large droplets created in the scrubber, the increased pressure drop usually results from a buildup of material on the mist eliminator surfaces, narrowing the openings for the gas to flow through. The resulting higher gas velocities can drag the collected liquid through the mist eliminator and back into the outlet gas stream, reducing collection efficiency. A decrease in the pressure drop across the mist eliminator may indicate structural failure. The performance of the mist eliminator can also be evaluated by observing the stack and areas adjacent to the stack. Rainout of droplets around the stack, mud lips, and discolored streaks at the stack discharge, or heavy drainage from open ports, all indicate a poorly performing mist eliminator. Finally, component failure records should be evaluated. An increase from the normal failure rate indicates that the source should carefully evaluate the cause and correct the problem before equipment damage and excessive emissions occur. To review, to determine if a wet scrubber system is working properly, field personnel should observe, if possible, outlet gas stream opacity, but take in consideration the presence of water droplets, the temperature difference between the gas inlet and outlet, the liquid flow rate into the scrubber. Other parameters include pH levels of the inlet and outlet liquids, and pressure drop changes in the wet scrubbers and mist eliminators. As with any inspection of an air pollution control device, attention must be given to the system's records and physical condition, and compliance with applicable rules. Wet scrubber systems used for air pollution control have many safety considerations, including inhalation hazards and corrosive liquids. Further training and experience will be necessary to complete all field tasks safely.